This computer. Yeah, Anna, I know it must be really hard on you guys having to deal with the Zoom. Hopefully this will be the last semester. I know it's hard on everybody, especially people that are out in Texas. That was tough. So let's, but of course this course isn't crappy. Let's see. Yeah, thank God. So today we talk about stellar evolution. That is, oops. Oh, come on. Stupid computer. Let's try that again. There we go. Stellar evolution. Brand, you were the shining light for me this semester. Well, I'm the shining light because the sun produces that light, and the sun produces that shining light through nuclear fusion, which we'll be covering today. Yeah. Okay. So today we'll be covering stellar evolution. Now, again, astronomy is a historic course, and we use the term evolution very differently than you use the term evolution. You use the evolution to talk about how different individuals of a particular species change over time and perhaps even become different species. In astronomy, stellar evolution is meant to talk about not how individual stars, how different generations of stars are different from the previous generation of stars, but how an individual star changes over its lifetime. So for us, we would call that the lifetime of the star or the lifetime of the individual. But for some reason, astronomers talk about evolution of the star. So again, it's another time when astronomy uses a word in a slightly different meaning. So I know you all love equations. We're covering 3 equations today. We'll be going over this fairly slowly. Before we get into stellar evolution, I thought I'd mention a little thing that's happening with Betelgeuse. Do stars have an average lifetime, or are they all different? Christine, that's what this entire lecture is about. You're going to love it. So does anybody know what I'm referring to here? Be afraid, be very afraid. Any guesses about what this refers to? The musical. Good guess. No. Supernova. Julie, that's exactly correct. Supernova, which star? I'll give you a hint. Think Michael Keaton. Batman. Yeah, Betelgeuse. That's correct, Julie. This is a picture of Betelgeuse in January 2019 and December of 2019. And unfortunately, Betelgeuse is now behind the sun, so it's difficult to get shots of it, but we think it's continually changing. Betelgeuse is changing, is getting dimmer very quickly. Why is this a concern? It's a concern because Betelgeuse is going to go supernova any day now. And by any day now, I mean anytime like today or a million years from now. So again, astronomers have a different definition of any day now. But if Betelgeuse blows up, it will blow up as a supernova. A supernova is anywhere from 1 to 100 billion times brighter than a normal star. Let me repeat that, 100 billion, but that's B with a B. So 10 to the 9, 10 to the 10, 10 to the 11 times brighter than a normal star. Typically, a supernova will outshine its parent galaxy that has 100 billion stars. It's the most energetic thing that we know in the universe, other than a hypernova, which is just a really, really big supernova. And supernovas blow up instantaneously. The explosion happens over a period of seconds, and we see it shine at extremely high intensity for several months. If Betelgeuse goes off, it's not so close that it's going to destroy us, but it is so close that it will outshine the moon. It'll be the most spectacular vision on the sky that's ever happened in recorded history. And so Betelgeuse is doing something weird. We don't know what it's doing, but it could very well blow up tomorrow. okay? So just thought I'd pin that up, look it up, and you know, everybody is guessing. Have your betting pool, whether it's going to blow up today or 20,000 years from now or 100,000 years from now. But like I said, for astronomers, that's all like today. Okay. And notice that the Betelgeuse right now is bigger than the orbit of Mars. It is one honking big supernova. For those of you that don't know Betelgeuse, imagine if I'm the great warrior Orion, okay, and I've got a belt that you can't see, and I've got my arm up here, and I'm kind of sloping. A Betelgeuse is the big bright, well, less bright now, the big bright red star in the top shoulder there. Okay. So today we're going to do a review of what we covered last time. If a supernova happened where the sun is, you would be on the Earth. It would be, yeah. So luckily, our sun cannot go supernova. It's just physically impossible. Our sun is too small. If our sun did go supernova, that's a bad day. I'm not sure that there would be time enough for the sense to go from our eye to our brain before we are converted into our constituent atoms. Actually, more than that, the atoms themselves would be ripped apart. Not only that, but if there was a supernova within 20 or 30 light years away, and the closest star to us is only 4 light years away, it would destroy all life. It would sterilize the planet. So supernovas are dangerous, really, really dangerous. And luckily, there's no star that can go supernova that's within the danger range. So today we're going to review what we covered last time in terms of stellar birth and structure. We'll talk about stellar mass and the lifetime of stars. And there was someone asked about lifetimes up here someplace. Anyway, we're talking about lifetime. We'll talk about evolution of the sun, which is not the evolution of stars. It will be how the lifetime of the sun, although we call it evolution. We'll talk about stellar clusters because stellar clusters are very useful for figuring out how stars live and how they die. And we'll talk about variable stars. And then we'll have a quiz, ungraded. Okay, lots of questions today, but they're all ungraded. So remember, stellar structures, stars start off as big balls of gas and dust. Something forces them to collapse. And as they collapse, that collapsing increases the pressure of that gas of ball and dust. And just like a diesel engine, as you increase the pressure, you increase the temperature. So here we go. The ball of gas and dust collapses, and as it collapses, notice that the central temperature goes up, the diameter goes down as it collapses and gets smaller and smaller. You are not responsible for the individual stages. You are responsible for the fact that we start with a ball of gas or dust. We turn what's called a protostar that heats up and shines thermally by just the collapsed pressure, the gravitational collapse, just like a diesel engine. It's just that compression, in this case caused by gravity as opposed to a diesel engine where it's caused by mechanical pressure, but compression caused by gravity that heats up the material and causes it to glow. And so here we have the central temperature of the protostar, and here we have the surface temperature. This is what we observe. When the central temperature reaches 10 million degrees, then a star is born. What we have is nuclear fusion sets off hydrogen to helium, and it now glows not by gravitational collapse, but by thermonuclear fusion at its core, which is the way our sun shines. In fact, all stars shine by thermonuclear fusion at its core. So here is mapping the collapse of the protostar into a star on the HR diagram. So over here are low temperatures, here's luminosities, and as the gas cloud collapses, the temperature goes up and up, and it has very high luminosity. It has high luminosity not because it's hot, but because it's very, very large. And if you remember, the luminosity goes as the radius squared times the temperature to the 4th power. Okay, so the fact that the radius is very high means that's why it's a protostar is going to be very luminous, although it's going to be very relatively low temperature, surface temperature. And then it will come down, it continues to collapse, the core gets hotter and hotter, And right about here, the core reaches 10 million degrees. A star is born, and then it settles on the main sequence. So this process takes millions of years, and then it will settle on the main sequence. For a star like our sun, it will take 10 billion years just sitting in the main sequence. Here are the birth lines for stars of different masses. And uh, one thread through this lecture is going to be that um, with stars, mass is everything. If I can tell you the mass of the star, I can tell you everything there is to know about the past, present, and future of that star. Contrast this to humans. If you know the human's mass, you don't necessarily know their past, present, and future. But it is true with stars. Stars are much simpler than people. So here we see the lines going from birth lines for protostars of various masses. These numbers here refer to how long it takes to get born. Okay, so a 15 solar mass star takes only 160,000 years to get born. And by born, it means you come on, you collapse, then thermonuclear fusion starts at the core, you settle down on the main sequence. But notice all of these stars, when they're born, the end point of the birth process to settle down on the main sequence. The main sequence is where all stars spend the majority of their lifetime. Okay. And the location that you wind up on the main sequence depends only on your mass. So here's this half a solar mass. It takes 100 million years to form. So it takes much longer to form than these guys. And as it crosses the birth line, it hits that 10 million degrees. And then it settles. If you're half a solar mass, you will settle here. And your lifetime is longer than we can measure. It's in the trillions of years. But you're very, very dim. How fast is a supernova? A supernova is, well, the core collapse itself happens in fractions of a second. The explosion itself, it then pushes out all the outer boundaries, and then the light will peak after a few hours, and it will stay at that peak as the remnants of the star that it was shine for months afterwards. But the explosion itself is basically, a second or two. Do the main white dwarfs stay in the main sequence as well? Absolutely not. We'll talk about white dwarfs in future lectures. White dwarfs are the end result of stellar death, okay? And white dwarfs form a cluster down here on the HR diagram. So white dwarfs are actually not stars because there's no thermonuclear processes happening in them. They're stellar remnants. They're the ash. That's what's left over after the star has lived a good life, and now they're settling down for retirement. And that retirement is down here. Okay. Sources of stellar energy, we went over this before. For our sun, it's hydrogen to helium using this very complex process that you are not responsible for. Yeah, that's right, a celestial retirement home. For stars more massive than our sun, we have what's known as a CNO cycle. Okay, and we'll get to that for a second. So in our sun, this happens to what we call the proton-proton chain. For the purposes of this course, proton-proton chain and hydrogen to helium are synonymous. Okay? In stars more massive than the sun, we have carbon goes to nitrogen and oxygen. It's also known as the CNO cycle. That doesn't really happen in our star. Our star is not big enough or hot enough for that to happen. Okay. And this is just a refresher from last time. The way that we understand stars are working is we just use the basic laws of physics, such as hydrostatic equilibrium. We know that every layer of the sun must be balanced, just like every layer of the Earth's atmosphere must be balanced. If it's out of equilibrium, you get thunderstorms. But in general, the sun, stars, and the Earth have to be in hydrostatic equilibrium. Energy must be transported through the sun, or energy would build up. And we know the energy doesn't build up in our sun because the sun doesn't blow up. So the energy that's generated at the core must eventually reach the surface. And if all the energy is generated in the core, which for most stars is approximately correct, then 100% of that energy generated at the core must be exactly equal to the energy that's released at the surface. Because otherwise, if there was a difference, then energy would build up somewhere in the sun and the sun would blow up. Okay. Mass conservation, there's no mass gained or lost other than the mass that we can measure that's leaving the surface of the sun through solar wind. And then energy conservation. Okay. So let's start off with a quick question. Let's see. So, objects more massive than our sun form into stars. A, much slower. B, in about the same time. C, much faster. D, not at all. Okay, there seems to be some debate here between A and C, much slower or much faster. Okay, let's go back. Look here. Stars much more massive than the sun take 160,000 years. Stars less massive than the sun will take 100 million years. So the more massive you are, the faster you're born. The more massive you are, the faster you're born. It's just because gravity has much more oomph when you're big and fat, okay, than when you're skinny and small, okay? And so, Micah, that's correct. Not only are you born faster, but you die faster, okay? So if you're really big and fat, say you're 15 solar masses, you form very quickly, you burn really bright, 1,000,000 times our solar luminosity, but you only burn really, really short amount of time, just a few million years. And then when you die spectacularly. You die in a supernova explosion that blows apart your entire friggin' galaxy, okay? So live hard, live fast, and die young, okay? That's their motto. Okay, that's the review. Now let's talk about stellar mass and lifetime. So here is the main sequence again. Here are all the regions. The main sequence is 90% of the stars we observe in the main sequence. We have the giants and the supergiants we'll be talking about in a bit. These are stars that are on their way towards death, okay? This is, if you're a giant or a supergiant, you don't have much longer to live. And then the celestial retirement home is the white dwarfs down here, okay? Where there's no thermonuclear fusion going on. These are basically the remnants of the cores of these stars. Of relatively low mass stars like our sun, because if you're high mass, there's nothing left over because you just blew kablooey, you just blew yourself to bits, okay? So here is a map of the fact that the vast majority, so these 3 shades of red are all stars that are less massive than our sun. And so that would be down here, okay? What we call the M-class stars or the red dwarfs. It's also called the red dwarfs. So if we go from relatively close to our mass to really, really small, I mean, look at that. To add those 3 sections, that's the vast majority of stars. Stars that are similar to ours are only 1 to 2% of the stars out there. 2 to 4 solar masses, only 3%. And then the blue giants, the really, really, the blue giants and the blue supergiants, it's like 0.3%, 0.06%, okay? And those would be up here. The thing is, these guys are so mind-blowingly bright that when you look at the night sky, this is most of what you see. So the majority of the stars you see in the night sky are going to be bluish or whitish, and they're blue giants or blue supergiants, and they tend to be far away. They tend to be really bright. And these guys down here, which are as common as stardust, we don't see them because they're just so dim. I mean, look at this. Here we're talking about 1,000,000 to 10,000,000 times the solar luminosity, and here we're talking a 1,000th solar luminosity. These are very difficult to find. Okay. Now, there's 2 things here that were discovered empirically. Okay, and these don't show up. If you remember the HR diagram, You got luminosity, you have temperature, and then you have radius. Now I'll show that in a second. In fact, well, actually, let me show that now. So where is that? Okay, and so remember the HR Explorer, we've got luminosity here, which is a logarithmic scale. We have temperature, and because L equals R squared T to the fourth, if I know the luminosity and I know the temperature, then I know the radius. And you can see here the radius lines here. So one solar radius line there intersects the main sequence line. So, and here is the main sequence. There's the giant supergiants, white dwarfs. And so as we go up here, these are larger physically, and these are smaller physically. So if I go to different temperatures, see the star gets bigger and smaller for the same luminosity. And if I keep the same temperature, but different luminosities, so it looks the same color, but it's bigger and smaller. And that's just luminosity equals R squared T to the fourth. What type of star is the North Star? Roxy, I don't know. That's a good question. I honestly don't know the answer to that. Okay. And you can play with this diagram. Woo, 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 woo. Sorry. One's got to have fun. Okay. But not on that chart are these two things, that the radius is actually proportional to the mass on the main sequence. So as the mass gets bigger, the radius gets bigger, and you can kind of see that along, oh, I'm sorry, let me show you that again. Okay, so as the mass will increase as we go up the main sequence here, and it increases as we go from here to here. Okay, let's reset this. As we go from our sun up to here, you can see this is approximately linear. We go from one radius, one luminosity, one radius up to 10 radii, more or less. And from here to here is also about 10 solar masses. So up here, it's a radius of 10 solar radii and a mass of 10 solar masses. Okay, so just by eye, this radius is proportional to mass for the main sequence kind of makes sense. Let's go back to there. And you think, why should I care? You should care because of what's happening next. The luminosity, how bright it is, goes as mass to the 3.5 power. So when we go back to this chart here, as I'm going along the main sequence, you can see that the luminosity goes from here, luminosity is 1 to a luminosity of 10 to the 5th, 10 to the 6th, while the mass goes up by a factor of 10. Well, 10 to the 3.5 power is about 10 to the 5th, okay? So this looks linear, but it's linear on a logarithmic scale. And so it just turns out that the luminosity, the radius increases in proportion to the mass as the mass goes up the main sequence. And the luminosity on the main sequence goes up as mass to the 3.5 power because this luminosity is a logarithmic scale. Okay. So I'm spending a lot of time on this. These two, since these relationships were discovered, they now have a theoretical basis for that. But for the purpose of this course, this was just an observation. It's an observation that the regime on the HR diagram called the main sequence, where most of the stars spend most of their time, has these two correlations that are really good. Okay. So if you double the mass, the luminosity will go up by a factor of 2 to the 4th power, basically, a factor of 16. Okay. Got that? 10 to the 3.5 power is equal to 10 to the 5th. Yeah, no, not quite. It's closer to, well, it's obviously 10 to the 3.5 power. I was speaking loosely. Yeah, you're correct, Matthew. So let me look at that chart again. It starts at a luminosity of 1 and it goes up to a luminosity of, about 10 to the 4th. Yeah. So, yeah, so Matthew, it's very approximate. Again, this is what they call an empirical relationship. This is not a pure relationship. And it's interesting because this textbook lists the mass going at 3.5 power. Other textbooks listed as m to the 4th power. So, yeah. So Matthew, you're correct. It's 10 to the 3.5 power. So how does this relate to the lifetime of stars? Well, the lifetime of a star is going to be the amount of energy it's got in the star so this would be like erg, this would be like joules, divided by the luminosity. Luminosity, remember, is joules per second, okay? So if you divide the total energy that's in the star by how fast it's getting rid of that energy, that will give you your lifetime. And the energy reservoir is the mass, because remember, you're burning mass. It's just like burning wood in a fireplace. So the time scale, the lifetime of a star is directly, hold on a sec. Oops. The lifetime of a star is proportional to the mass divided by the luminosity, because the mass is how much stuff you've got to burn, and the luminosity is how fast you're burning it. So the lifetime of a star goes as the mass of the star divided by the luminosity, which, as we just said, goes as 3.5 power, m to the 3.5 power. So the lifetime of stars is approximately the mass to the 1 over the mass to the 2.5 power. So the life expectancy in the main sequence depends on the mass to the minus 2.5 power. What this means is the bigger you are, the harder you fall. In other words, your lifetime, if you're very high mass, is very short. Your lifetime, if you've got a low mass, is very long. And because of that minus 2.5 power, it's a very, very steep curve. So here we go from O, B, A, F, G, K, M, the spectral class. Here are the masses, okay? 40 solar masses down to 1 solar mass, down to half a solar mass, okay? And so this is not a huge range. I mean, this is a range of like 80 to 1 for mass. Next, look at the luminosity. The luminosity goes from 400,000 to 0.05, and that's a factor of several million, okay, in terms of luminosity. And so the fact that the sun's luminosity is a positive 3.5 power of the mass makes sense looking at this chart. Look at the lifetime. An O star has a lifetime of 1 million years, a B star 10 million years. R star is 9 times 10 to the 9th. That's about 9 billion years. K star is 20 billion years, and an M star is 100 billion to a trillion years, okay? So notice how incredibly steep this is. There's not a huge difference in terms of masses, but there's a huge difference in terms of the luminosity and a huge difference in terms of your lifetime. You know, burn fast, burn hard, die young. That's the big stars. Whereas the M stars are, yeah, let's just chill out for longer than the lifetime of the universe. I mean, here we're talking about 100 billion to a trillion years of lifetime. And the universe itself has only been around for about 13.7 billion years total. So we're talking about stars that have a lifetime that is several universes' lifetimes to go. Okay. So the main sequence is where stars spent 90% of their life. We've showed you the birth onto the main sequence. The mass on the main sequence goes from 0.1 meter solar masses to 120. This number, there's a lot of dispute about this. Some astronomers think that number is 50. Some astronomers think that number is 200. And it's complex. It really depends on which galaxy and stuff. The luminosity varies as mass to the 3.5 power. You're not responsible for calculating this equation. You are responsible for knowing that it's a very steep function, that stars that are more massive are much, much more luminous. And the lifetime varies as mass to the minus 2.5. Again, you're not responsible to do this calculation. You are responsible to know that it's very, very steep, that the big stars last 1,000,000 years, the little stars last trillions of years, okay? And the radius goes as the mass. And the spectral type, OB, AF, GKM. OB are the really bright blue stars that burn bright and die young. G stars are like us, and K and M stars are those common as stardust red dwarfs that last forever. Okay. So now let's talk about our sun. And remember, what your past, present, and future is depends solely on your mass. So what we're going to talk about is just the past, present, and future of stars that have the mass of our sun. Later on, in future lectures, we'll talk about the evolution of stars that are larger than our sun, because evolution of stars larger than our sun tend to be explosive, okay? So the evolution of our sun, remember, here are three numbers to remember: 10 million degrees, 100 million degrees, and 600 million degrees. When the core of the sun reaches 10 million degrees, a star is born, okay? And this is even better than Bradley Cooper and Lady Gaga. 10 million degrees, this is really beyond red hot. That's when hydrogen fuses to helium, and that's what's happening in the core of our sun right now. When the core of our sun reaches 100 million degrees, then that hydrogen, the helium, will now burn into carbon, okay? And that has not yet happened with our sun, but it will happen with our sun. If the sun's core ever reached 600 million degrees, and then we have that CNO cycle, we would have carbon burning to nitrogen and oxygen. That will essentially never happen to our sun because our sun isn't big enough. So it's only the first two levels that happen. And so what eventually happens is the core of our sun builds up a bunch of carbon that never gets hot enough to fuse. And what we're left with is a carbon core. And what our sun will eventually die to become is a carbon white dwarf. Okay. But what's happening now is, will there be a dramatic change in our sun looks when our sun switches over to helium? So Bennett, yes, there will be a dramatic change. We will not be here to see it, however, because by then the sun will have engulfed the earth and completely destroyed it. We'll be talking about that in a future lecture. So the core converts hydrogen to helium, and hydrogen burns in the shell. So what happens is, our sun currently has this tight little core that's helium that is not yet at 100 million degrees. So it just sits there, it's ash. Surrounding that ash of helium is a shell of hydrogen that's fusing. So you've got ash that's not doing anything surrounded by a shell where all of the fusion happens, okay? And here is a diagram, and the core is really, really small. It's really, really small. So here is the radius of the sun in Earth radii, not in solar radii. So the sun itself is about 80 Earth radii. Okay, but at 0.1 radii, so a tenth the size of the Earth, is the helium core, and then this blue region is the helium burning. I'm sorry, the hydrogen burning shell, right there. Okay, and you would not be able to see it on this scale. So the core where all the action happens is tiny, tiny, tiny. So if we move to another planet, could the human race survive, or would we have to go outside the solar system? So Nikki, if we move out to Pluto or maybe one of the moons of Saturn, we might be able to survive. But we're talking about, a few billion years in the future, and we'll cover that in some detail in a bit. Okay. So yeah, what did Babylon 5 say? Oh, the sun. No, our sun cannot go nova. It just can't. So in fact, we'll talk about nova. And in fact, that is just a misunderstanding of the word nova. A nova can only happen on the surface of a white dwarf with a companion star accreting onto it. And our star doesn't have a companion, and it's not a white dwarf. So so we've got the helium at the core, and this hydrogen fusion cell. Now, over time, this whole thing gets hotter. It gets hotter because you've got the helium, it's not doing anything, and it just compresses and it compresses and it compresses. And as those compress, it gets hotter. And so I don't know what the temperature of a core is, but it's more than 10 million degrees. And then when it reaches 100 million degrees, all heck breaks loose. We'll talk about that. So as the hydrogen shell gets bigger, okay, as that shell gets bigger, what's happening is it's burning more hydrogen, because the bigger the shell, the more hydrogen that's exposed to the shell. And the more hydrogen that's exposed to the shell, the more energy it produces and the hotter the sun gets. Our sun has increased its luminosity by 30% since the planet was born. Okay. So when life first developed on the Earth had much less sun hitting it. And that will increase. Our sun will continue to increase its luminosity over the rest of its lifetime, because that shell gets bigger and bigger. And when that shell gets really big, what happens is that core is generating so much energy that the sun has to expand to allow that energy to escape. Okay. And that becomes a subgiant, and then it becomes a red giant. So our sun will eventually grow to become a red giant. And the radius of the Earth's, the size of the Earth's orbit is about here. And so when you become a red giant, you have already engulfed the Earth and you've destroyed it. And this will happen somewhere around 4 billion years from now. But as you continue, and so there's more that happens here. When you get to the red giant phase, the hydrogen becomes, the inert hydrogen becomes so hot that it reaches 100 million degrees. And when it reaches 100 million degrees, all of a sudden the helium starts to burn. So you got the hydrogen that's burning, then you get the helium that's burning, and it burns to carbon. So hydrogen burns to helium, helium burns to carbon, and we have what's known as the helium flash. And what happens for complex reasons is the star actually moves back down, and then it moves back up. And so you have this red giant, and then you got this little dance, and it becomes a double shell burning red giant. You don't need to know that phrase. You do know that this is called the asymptotic branch. So the sun goes up the red giant, back down, and then back up as it's starting to burn helium. And then not a lot happens. The sun becomes so large that it starts to spew off its outer atmosphere. And that outer atmosphere is called a planetary nebula. And the Milky Way is lousy with them. I can show you pictures that I took with my telescope of planetary nebula. Let's see if I can bring one up I took just a couple weeks ago. Yeah, here we go. So here's a photograph I just took with my fancy telescope. Okay, well, this was in November. I think I took a more recent one. And this is a planetary nebula you see here. And what it is just a bunch of glowing gas that's blown off from the atmosphere of dying stars. Okay. Let's see if I can find another shot of that. Oops, sorry. Yeah, here we go. Yeah, there's a better photograph of the Dumbbell Nebula, and I took this just before Christmas. And then here is another planetary nebula, and this is called, not surprisingly, the Ring Nebula. Okay. So let's go back to the keynote. And so different stars have different pathways as they're dying. So when you talk about very massive stars, they don't follow this path. They all follow different paths. And these really bright stars, such as Betelgeuse, they don't settle down as we showed here, where you blow out the planetary nebula, and then that carbon core that's left over then just kind of settles down and becomes a white dwarf. Okay. So stars like our sun have, except for the fact that they destroy the Earth, have a relatively quiet death. Okay. They expand a lot. They blow off their atmosphere. They produce these nice glowing balls of colored gas in the galaxy. and then they just kind of shrink and become white dwarfs, and they retire. And our galaxy is lousy with these white dwarfs. They're not very luminous, and they're really, really small. They're about the size of the Earth, so they're hard to find. Stars like Betelgeuse blow up. So hotter stars are more likely to become supergiants. Well, yeah, so all stars, when they die, become giants or supergiants. The thing is, stars like Betelgeuse, uh, the supergiant phase is the precursor to the supernova explosion. Okay, so stars more massive than, say, about 10 solar masses all blow up. They don't have a nice retirement. They explode, and when they explode, there's nothing left. Okay, so a star that will spend most of its shining lifetime: A is a protostar, B is a red giant, C is a main sequence star, D is a white dwarf, E evolving from type O to type M. Okay, and you all got this correct, that a star spends 90% of its life as a main sequence star. And here's something I didn't emphasize, but is really important. A stars continue to evolve during the main sequence life. A, they gradually become cooler and dimmer. B, they gradually become hotter and brighter. C, they don't change their spectral type. Glad I have this question, because I can't believe I forgot to emphasize this. So here's the thing. The correct answer is C. Once they've been born and they sit on the main sequence, they stay on their specific spot on the main sequence for 90% of their life. So they follow this elaborate path to be born. They then sit on the main sequence, and they sit on that main sequence until they're about ready to die, until they become a red giant, a red supergiant, and then a planetary nebula and a white dwarf. Okay. So while they're on the main sequence, they typically don't move. Okay. So what inevitably forces a star like our sun to evolve from being a main sequence star? A, the core begins fusing iron. B, the core uses up its supply of hydrogen. C, the carbon detonates and explodes as a type 1 supernova. D, the helium builds up at the core while the hydrogen burning shell expands. D, the core loses all its neutrinos, so all fusion ceases. And that's correct. The answer is D. Okay. And as the shell gets bigger, there's more burning going on, so it generates more energy. Okay. Okay. Before we get stellar clusters, let me show you a couple of things here. So let's go to, shoot, where is that? Star in a box. Yeah, let's go to star in a box. Where is star in a box? Here we go. Star in a box. Okay. So let's open the lid. Here is the pathway of a star that's as massive as our sun. There's the size of that star. It goes up. Then we get the helium flash in a second, pops back down, goes up again. And then it does this relatively quickly. And let's see that at normal speed. Here's the size of the sun. Here's the temperature. You can see the temperature here, over there, and you can see the brightness there. You can see it's getting really, really bright and really, really big. Here's about where it eats the Earth. Snaps down, goes up again. And then as it comes across, this stage is relatively quick, and then it comes down and becomes a white dwarf. Let's try something with much, let's try a very small solar mass. Let's try even smaller. And the thing to notice here is 9, 10 billion years. I'm sorry, that's 100 billion years. Yeah, 100 billion years. So, and remember, our universe is only 13.7 billion years old. Okay, so we will never see this in our history. Now let's look at a really big star, say 40 solar masses. And then it blew up as a supernova. Okay, we go to 10 solar masses. And when we get these intermediate mass, the bigger stars, they follow a very complex path, but they all in supernova. Okay, so you're not responsible for these very complex paths, but you are responsible for the fact that really big stars blow up as supernova. And we have an entire lecture just on supernova coming up. Okay, so let's go back to our lecture. How long does a helium flash process take? It's very quick. I'm going to say just a few thousand years. Is ether like, what would that look like? So Nick, I'm not sure what you're referring to. Yeah, so very quick. So a few thousand years, maybe even quicker than that. So stellar clusters is really important for us to understand the way the universe works. A cluster, for the purpose of this course, is a bunch of stars that were formed at the same place at the same time. So they're the same distance and they're the same age. And this is really important. So other things vary, such as their masses. So and a specific type of stellar clusters are known as globular clusters. And globular clusters are important for two reasons. First of all, globular clusters are the oldest, consist of the oldest stars that we can observe in the entire universe. They're very old. Some of them are as old as 12 billion years. Remember, our entire universe is only 13 billion years old. The other thing is globular clusters tend to be clustered not in the disk, the plane of our galaxy, but surrounding our galaxy in a halo. And we believe that the globular clusters are leftovers from the formation of the Milky Way galaxy before it accreted into a disk. Okay. And so by studying globular clusters, we're basically doing stellar archaeology. We're looking back at the beginnings of the formation of our galaxy. But also because they're all the same distance and the same age, then that tells us a lot about stellar evolution. So how can you tell the age of a cluster from the HR diagram? Anybody have a guess? Remember, these stars live for trillions of years. Stars like our sun will live for 10 billion years, and stars up here will live for 1 million years. The turnoff point, that's correct, Michael. You can tell because the turnoff point. So Andrew, the thing is, if all of the stars in the cluster are the same age, and let's say the cluster is 10 billion years old, well, if you're a blue supergiant, an O star, you don't exist anymore because you blew up billions of years ago. Okay. So what happens here is this is a very young cluster. And a young cluster, remember that the birth stars take a very, if you have a lot of mass, you get on the main sequence very quickly. If you don't have much mass, it takes you a long time to get born. And you can see that here. These stars are protostars. They're still waiting to get born These stars have already been born. Okay, so this tells us it's a young cluster because they're on the main sequence, but the smallest ones have not yet reached the main sequence. But the reverse of that is also true. You can see as stars come off the main sequence. So let's watch this video. Let me turn on optimize for video clip.
This is a Hubble Space Telescope image of the crowded core of the globular cluster Omega Centauri. The brilliant colors of the stars are real. They correspond to stellar temperatures. They can also be used to trace stellar evolution. Astronomers like to know how blue the blue stars are and how red the red stars are. So we'll first sort these stars out by color, blue on the left and red on the right. Next, we'll sort the stars according to brightness, the brightest stars at the top and the faint stars at the bottom. The final plot you see represents different stages of evolution of stars. Stars spend most of their lifetime burning on the main sequence. When the fuel starts to run out, they expand to become red giants. They find a new source of fuel, helium, and burn blue hot, but even that runs out. They end up burning out as white dwarfs. Based on images for the Hubble Space Telescope, we've assembled a true plot that is a snapshot of the life history of stars in this ancient cluster.
Yeah, you're not responsible for horizontal branch. Just pass that on. Okay, so here, the turnoff point will tell you how old the cluster is. So stars up here are so young that they've already died, okay? And so the turnoff point is, so here are stars just being born. Here are the biggest stars have already died, and then they die more, and then they die more. So this turnoff point tells you how old the cluster is. So this is a 1 million year cluster, and it goes like there. Here we've got the turnoff point, and this is 100 million years old. This is 4 billion years old, and notice the turnoff point has moved down here. And so these stellar clusters, which are the same distance and the same age, tell you a lot about stellar evolution. So the turnoff point is where stars leave the main sequence, okay? And then they'll spend, some time in the red giant point. So the definition of turnoff point is when stars leave the main sequence. Our star, our sun, will leave the main sequence in about 4 billion years from now. And then it will spend another few 100 million years in the red giant phase and the blue horizontal branch before eventually becoming a white dwarf. Okay, so let's skip these questions because we're running out of time. So let me talk to you a little bit about variable stars. So there are particular stars that vary in magnitude. They get bright and they get dim, and the time that they get bright and dim varies. So they get bright and dim over a period of days. And so because this is a human time scale and these stars tend to be fairly bright, we've known about these variable stars since antiquity, that we can see these stars get brighter and dimmer on a periodic basis, okay? And why they get brighter and dimmer is way, way beyond the scope of this course. It has to do with instabilities and the convection zone, the radiative zone. But anyway, the point is that these particular stars vary in a predictable way and a particular time scale. And in fact, there's what's known as instability strip, stars that are in the process of dying but have entered this instability strip. And notice that stars, we say they don't spend much time here, but our definition of not much time is a few million years. So stars that are in this instability strip will produce these oscillations. And here's the key point. The time frame of these oscillations depends on how bright it is, okay? So, and they're called Cepheids. They're also called RR Lyrae stars. And so for stars of this particular type, the oscillation frequency, which you can measure easily, I mean, you don't even need a telescope. You can just look up the eye and says, oh, it's magnitude 4 now, and then it'll be magnitude 3. You can measure this oscillation frequency very easily. That oscillation frequency will tell you the absolute brightness of the star. So all stars, all Cepheids that vary with a period of 50 days will be exactly the same brightness. And so now we have a way independent of parallax, to figure out the absolute distance to a certain class of stars. And because these Cepheids are very bright, we use these Cepheids to figure out the distances to particular parts of the Milky Way galaxy and to the distances to other galaxies. And so just by a quirk, that some of these red giants will oscillate with a frequency that depends on its luminosity, means that we have an independent way to set the distance to these stars and hence the size of the universe. And so these particular stars are really, really important. Why do they oscillate, Matthew? Answer number one, it's way beyond the scope of this course. Answer number two, which is more pertinent to this course, is I don't know. It's like so let's say that you put water on top of oil, for example. Well, that's unstable because the oil wants to be on top, and so you're going to see an instability as the oil flows up to the top. In fact, convection is considered an instability, because you're hot at the bottom, cold at the top. But clearly, there's much more going on. The fact that this instability happens over 50 days. So it's a fluid instability. I don't know the details. Sorry. So that's it. I'm running out of time. I have a whole bunch of quizzes, but let's skip that in the interest of time. I'll open it up for questions. You can turn on your mic, and don't forget the exam is Thursday. Questions, comments, concerns? Pet videos you want to share? Yeah, thank you. Can a nova explosion cause star clusters everywhere to form? Yeah, so Jacob, that's an interesting question. So typically a supernova will produce a massive shockwave, and we do believe that sometimes those massive shockwaves will produce a cluster of stars. So I think the answer to that is yes. Okay. If you create a company that made telescopes, would they be considered the name brand? That's cute. Yeah. Let's say brand X. If K&M stars haven't died out yet and O and B stars have, does that imply that the portion of O and B stars in the universe was higher a long time ago? So Matthew, that's a really interesting question. We believe the answer is probably no. So the O and B stars that we see today haven't recently formed. And so really the question you're asking is, has the rate of star formation changed as we go from early universe to late universe? And the answer to that is most definitely yes. 90% of the stars that can ever form have already formed. But that said, star formation is still going on. Gas and dust in galaxies is still forming stars, especially when galaxies collide. So Matthew, I don't have the absolute answer to that, but I believe the answer that not only but I don't think anybody knows the answer definitively on that. But we believe that stars typically form with similar amounts of. Oh, that's interesting though, because you're right that the K&M stars that were formed back then should still be around, whereas the O and B stars are continually forming. You might be right. Let me read about that afterwards. For the study guide, what do we need to know about convection in regards to this particular lecture? So for us, you don't need to know anything about convection for this lecture. What you do need to know is the layers of our sun in order, the radiative layer and the convective layer. Now, those layers are different for different masses of stars. You don't need to know that, but you do need to know the ordering of the layers of our sun, which includes the convective layer. What's the youngest star that's ever been discovered? So that would be in the Orion Nebula. We see stars that are in the process of being formed right now, that are right now being turned from protostars into stars. How can 90% of the stars that have already formed the universe is constantly expanding? So Matthew, stars are formed by gas and dust that's been compressed. And there's only a certain amount of gas and dust in the observable universe. And when that gas and dust is all turned into stars, well, then that's pretty much it in terms of star formation. Now, that said, stars do send off planetary nebulae. They do send off material into space. But in terms of primordial gas and dust, that's being used up rapidly. And in fact, universal expansion makes that even worse, because as the universe expands, that means there's less and less chance to compress that gas and dust to form new stars. Matthew, I'm going to have to think about your question. You might be right. I was thinking that the ratio of OB stars to KM stars will be the same throughout the entire universe. But since the KM stars that formed earlier are still around, if I add up not what is being formed now, but what exists now, you're probably right. Other questions, comments, confusions? You excited about the exam? So Matthew, what I'd highly recommend is my colleague at NC State, who also teaches this exact course, called Katie Mack, and she just came out with a book that is now a New York Times bestseller called The End of Everything, Astrophysically Speaking. It's a great book, a great read, and she talks about those exact issues. And in fact, the last lecture 23 is actually a modification of her lecture on The End of Everything. So certainly, so does that, of course. Yeah, and I think that the great freeze theory that you're talking about is the most likely outcome. But Katie also lists other possible outcomes for the history of the universe. Any last questions? Okay. If not, I will, well, I won't see you Thursday, but enjoy the exam on Thursday, and I'll see you a week from today. And enjoy the rest of your week, and enjoy the exam. Thank you. Thanks to all. I love teaching this course. Better than having a parakeet go nuts on me. In fact, let me show you that parakeet. This is the bane of my existence. That's Tony. Tony loves to be on my keyboard all the time. Okay. Thanks so much. I'll see you.